Okay, here we go. Uh, let's continue to talk about 5.3. It's called the definite integral. And um, in this section, I would like to introduce the broad idea, okay, the big picture about, how do we interpret the definite integral. And, are there some connections with what we covered from 5.1, right? The uh, approximation for area under the curve, like this. And, okay, so let's do some review, guys. Think about it this. In 5.1, when we're trying to do the approximation for the area under the curve, for example, we have fx equals x squared, and the interval is from 0 to 4. I already draw this, okay? And the area under the curve, as you can see that it's this part, okay? How do we do that? If you still remember, what we can do is we can partition our interval into four equal lengths, right? And then we use the height. Remember, we use the right hand side, the height, right? And so maybe use smaller one, right? Something like this, right? Remember, this is what do we describe? We use the right hand side, and then to form those, oops, rectangles, right? And then we calculate those areas of rectangles, add them together. This is the approximation. And if we double the number of the partition, if we partition 8 pieces, right? Good. And you will see that still we can use the right hand side, the height as a height for each rectangular. Then if we add them together, it will be better. So every time if you increase the number of the partition, the result is refined. It's getting closer to the real area end of the curve. Okay. So now let me briefly introduce the idea. Is called the Riemann sum. Okay, a Riemann sum. What Riemann sum says is like this. So when we do the partition, let's randomly do the partition. In this part, it's an equal length, right? What we can do is equal length. But you can see in this part, well, from 0 to 4, if I want to partition into 4 parts, I just randomly, put 3 numbers between 0 and 4, so I can form, 4 parts, right? Part 1, part 2, part 3, part 4. And remember, on the first, on this part, we use the right hand side, the value to be the height for each rectangular. But when we try to construct a Riemann sum, you see, guys, if this is, let's see, if this is a graph, okay? Again, guys, trying to understand the big picture. Before we use the right hand side height as a height of a rectangular, but during the Riemann sum, what I can do is, okay, I can pick any number as long as it is in my first interval, okay? Suppose I pick the height is like this, okay? Oops, let's see. Let's pick a height in the middle. So you see, for the first part, this is my rectangle, okay? For the second one, again, any arbitrary height. For example, something like this. This is my second rectangular. The third one, I don't know, maybe pick height here. So you can see that this is the area for the third piece. Fourth one, well, maybe I pick the height here, okay? So as you can see that this is going to be the area for the fourth piece. Now this seems like a nonsense, but guys, think about it this, okay? If I increase the number of the partition, okay, let's say let's have 8 partition, 16 partition, 32 partitions, 64 partitions. Do you realize that with the number of the partitions of the interval goes up, actually each interval, even you don't have to be restricted, but as the number of the partitions goes higher, what if we have like, let's see, 10,000 partitions, right? And you will see that each interval, each partition interval, it's gonna become smaller. No matter you partition it evenly or unevenly, okay? And also correspondingly, when the number of the partition goes super high, and then you will see that to the very end, it gonna become almost like one vertical line, right? Because the interval is super tiny. And in this way, if you add the number, if you add the area of those small rectangles together, okay, and if you take the partition number, take a limit. In other words, let the limit n goes to infinity, okay? If the sum of the area exists, okay, and then that area, we can denote it in an integral way. That is, we can denote this process as integral from 0 to 4 x squared dx. Okay, so this is what we call the definite integral. Okay, it started from 0, right, and at 4 x squared, which is the corresponding function, take the integration with respect to x. This is called the definite integral. Indefinite integral, we know that we introduced from 4.8, which is x, right? Integration x squared dx, and we know this part is x cubed over 3 plus an arbitrary constant. This is called the indefinite integral because there is no start and an index. But definite integral has a starting index and also has an end index. Okay, x squared dx here. And how do we do this? This is something what are we gonna learn in 5.4. But I just want to let you to know the basic idea. The Riemann sum, guys, which is you partition the interval, no matter even or unevenly, you pick any height inside of each interval, you add all this together. This is what we call a Riemann sum, okay? And if you take the limit of the Riemann sum, okay, if that limit exists, okay, and we call that this can be interpreted as one definite integral. Also, we also call that this function is integratable on the interval from 0 to 4, okay, from 0 to 4. And if a function, it is continuous, okay, on the interval, or it has finite discontinuity on this interval. In other words, you can have one discontinuity, there is a jump, or you can have 2 discontinuity, that's okay. But you cannot have infinitely many discontinuity on this interval, okay? So in our class, and the problems you handle, I will see that 90% of the problem will be, the function is continuous already. So they're gonna be integratable, okay? So that's kind of like the big picture about the 5.3. Also, guys, you can also think about the meaning of the definite integral also in this way. If we have a function, that function is a non-negative function. In other words, the function is greater or equal than 0, so like this, okay? Then this definite integral from 0 to 4 x squared dx stands for the area under the curve, okay? Area under the curve. Well, now maybe let's think about it like this. Let me erase this part. Okay. So if we have, I don't know, something like this, okay. This is a function, okay? And then it's from A to B, okay? And if we denote this is fx, you can see that it is continuous, okay? So the definite integral from A to B, fx dx, what does this part mean? And as you can see, guys, if we put, I don't know, put here as a number c here, you will see if this integral, if I do an integration from c to b, do you realize that based on what we just talked about, so that integration stands for the area under this curve, right? Now think about into this. If a curve is below the x-axis, you can treat the area as a negative, okay? So that's kind of like the definition. Because you think about this part, when you do the partition, we multiply the height actually is negative. Okay, so this integral from a to b fx dx, you can think about it, it's the area of the top doing a subtraction of this area, okay? Assume this area is positive. Or if you have the definition, if it's above axis, area is positive, below x-axis, area is negative, you can think about it, it's the area from A to B. Because this part we already treated it as negative, this part is positive. Okay, so that's the definition. And also, as you can see that this part you can split this integral into from A to C, fx dx, plus from the integral from C to B, fx dx. As you expect, from C to B, it's gonna be a positive, right? From A to C, it's gonna be a negative. Okay, so I'll stop here and then we'll move on.